I'll be talking about the graphics virtualization in the upstream Zen. As Ian was talking about yesterday, SCI project has been going on since 2007. So last year, my Intel colleagues, Wei Dong and Ben Lin, has checking some base changes into the Xenon stable. And then over the years, during the SCI work, we have been on the, acting as a consultant, to the all the work that they've done in the graphics virtualization area. So at the beginning of this year, when they were having problem bringing up the graphics device on the Capella system, I got involved, bring up the integrated graphics on Capella. And later on, after we resolved that, we went on getting things working in the Sandy Bridge. So we were talking. In this talk, we'll talk about the problems we encountered and also the changes we made to get things working. So the main purpose of this talk is to get you to understand what kind of issues we encountered, and then the changes we're making. And in order to do that for graphics, I want to go through some of the basics, right, in terms of how the devices are initialized in the native environment, and then also when we have virtualization in the QEMU virtualization, how the flow works in that. And then moving on to the pass-through, when we add pass-through to these HVM, what kind of, how that flows different. So we're basically doing a build-up from the very basic level to the pass-through, and then followed by the graphics pass-through changes we made. So in the graphics pass-through topic, we'll start with the base changes we are making that will apply for both the discrete graphics and the integrated graphics. And then followed by the stuff, what's unique about discrete graphics, and then followed by the integrated graphics. The end, and then followed by the current status and future work. So here I just want to give a little high-level overview of what happens in the driver initialization. So when a device driver try to initialize a device, it has to find the vendor ID and device ID of the PCI device, right? Once they find the matching device, then it will initialize. It will map the control area using MMIO so that the driver have access to all the control registers. And then it will use the control register to initialize operations, such as a DMA operation, right? When it's trying to do a read or write. And then when the DMA operation finishes, and then you'll have a interrupt. The hardware will generate interrupt, and then it will get the CPU have a control again to issue additional operations. So that's the general flow of how things work. So now in the next slide, we're going to talk about how this works in the native environment. So in the native environment, one of the things the native environment uses is this CFA, CFC registers. And then the way it works is, it will write the bus device function and then offset, PCI offset to the CFA register. And then the hardware will automatically put the content of that offset in that particular device to the CFC. And then after that, the software will read it. And that'll basically how you get the PCI vendor ID or device ID from that device. And then based on that, you can then to see whether that matches what the device you're looking for. And then once you find the device, and then you can go map the control area to the MMIO with the MMIO mapping. So over here, we also talk about in some devices, in more of a legacy devices, they have these I/O port, right? So they use I/O port to access the control area. But for the most modern devices, you use MMIO accessing. And then so once you have this MMIO access to control the control area, and you can issue the DMA operations. So for DMA operation in a native environment, because on the I/O side you don't have a physical to virtual mapping, so the driver has to program the physical address into the device, right? So that the device can transfer data directly to the physical address the memory corresponding to the physical address. So that's the main motivation when on the device side, you have to use the physical address. And then once the DMA finishes, the hardware will automatically generate an interrupt. So this slide will talk about how this, in the HVM environment, how does it work when you have a QEMU that does the I/O virtualization. In the QEMU virtual platform, you have a bus 0, right? And then for all the virtual devices that's emulated by QEMU, you basically all the devices are hanging off on the bus 0. So you have 0, 1, 0, 0, 2, 0, and things like that. And then when they create these virtual devices, what they do is they basically create these PCI config memory for each of these devices. So for, let's say, if you want to create, in the QEMU, we have a E1000 NIC. And then what they do for the vendor ID, device ID, they'll have they enter A086 for vendor ID and then 10E for device ID. So those will be accessed by when the guest does a vendor ID, device ID read using PCI config, the QEMU mechanism will go and read these data off the config space and provide it to the guest driver. And so over here, we're saying that there's actually in the PCI device data structure, you have a configuration, basically a piece of memory array where it contains all these, PCI config information. And then as I say already, is that when the guest driver accesses those information, basically do I/O port reads of CFA and CFC, is automatically the information will be read off from this configuration area QEMU constructed. And for other I/O port reads and MMIO, those are all trapped by the QEMU and then emulated. It's similar to the DMA operations and the interrupts. Those are all basically emulated by the QEMU. And here's just more of a graphical illustration of what we just talked about, right? So you have a native driver running in the guest environment, and then you have a device model, QEMU device model running in domain 0, and that will interface with a driver, a real device driver in the domain 0 that does the actual I/O, which the QEMU will emulate. And then the communication between the guest and the device model are through the basically for the operations like native driver in the guest uses, you basically will be trapped by the hypervisor and forwarded to the QEMU, which will do the emulation. So here we're talking about, and now we go to add another step on top of that. Is basically when we have adding the device pass-through on top of the QEMU emulation. So when you have device pass-through, in addition to have these virtual devices emulated by QEMU, you will have this pass-through devices. And the difference between pass-through devices and the virtual devices in QEMU is that the PCI config area, you're actually reading off from the actual device. So let's say if you pass through E1000, so all the vendor ID and device ID are coming from the real device. If you pass through something else, like a USB controller, it'll reflect that also. So in terms of a config space handling, because we're exposing the vendor ID, device ID to the native driver in the guest, then the driver can successfully initialize. And most registers in the PCI config space are emulated, just like in any other virtual devices we talked about before. But for some registers, such as the command register, where you have to turning on and off the bus master bits, then those get passed through. The QEMU actually will say, hey, we need to pass this on, and it would actually go right directly to the hardware. So when you have for IO port handling, what we do in Zen is we actually, because of the fact that the guest IO port and the host IO port, they are different. They actually have a translation. So what we do in the Zen, we intercept whenever there's an IO port access for the pass-through device, we'll trap it, and it will translate it to the host IO port number, and then do the access on the guest's behalf. And then for read and writes, we just do that. We actually, before we do actual accessing, we actually check to see if there's a permission for it. Whether the guest has this permission to access these IO ports. And for MMIO handling is that for the MMIO, usually they are reported in the PCI bar. So once we determine it's an MMIO, we will do a guest physical to machine physical mapping. So that once it's mapped, the guest can access this area transparently. It will not cause additional VM exit. And then for DMA, once you have access to the control register, the guest will initiate a DMA operation. And then when the way we talked about earlier, the driver usually, what they do, they'll program the physical address to the device. Well, however, since in this case you're running in the guest environment, you're going to program the guest physical address, right? And then and because in the virtual environment, the guest physical does not equal to machine physical, then what we need is a hardware IOMMU to do the translation. That's where VTD and AMD IOMMU comes in. So that'll do the translation automatically. And then when the DMA finishes, you'll have an interrupt from the device, from the pass-through device. And in this case, the interrupt will get injected into the hypervisor, because the hypervisor owns the interrupt handling. And then once it gets the interrupt, and once it determines that this interrupt is from the pass-through device, you'll inject this interrupt into the virtual IO APIC, and which will propagate to the virtual local APIC. And then when you do a VM enter again, Zen code, hypervisor code will check the virtual local APIC to see if there's any interrupt pending. And then if there is, you'll program the VMCS to inject the interrupt into the guest. So that's the flow, how that works. So for graphics pass-through, we'll talk about, in this slide, we'll talk about what are the base changes. So pretty much, actually all the changes are in the QEMU and the HVM loader. So there's no changes in Zen. Well, one of the things that's different from the devices we passed through before, like NIC, is that we need to execute the video BIOS. Right? So right now we have a code to copy the video BIOS from the physical address C000 memory, copy the video BIOS from the device's C00 memory to the guest, so that guest at that point will contain the actual video BIOS, and then during the guest startup time, it will get executed. When it's actually in the HVM loader, and there's a video BIOS execution code in there. In addition to that, we also pass through some legacy I/O ports that are used by the video. So these are the 3B0 to 3BC and 3C0 to 3E0. I think those are for the EGA, VGA, those legacy devices. Another thing is that the legacy video MMIO range at A many zeros to BFFs. So in this slide, we're going to talk about the stuff that's specific to the discrete graphics. So for discrete graphics support, we're targeting the workstation graphics cards from NVIDIA and ATI. The NVIDIA cards is what we use is the FS3800, and ATI is a FirePro V3750. For NVIDIA device, so that particular family of devices are actually all very expensive, and the most cheapest one I got is the 3800, which costs about $900 each. And then this particular thing, when we talk about the video BIOS on this particular device, we actually have some problem executing it by reading off on the C00 area. So what we have to do is actually you need to apply a tool to manually read that off, and they get it built into the HVM loader in the BIOS, in the guest BIOS, and then that will work. That's the only way to get it work. However, it's kind of impractical to do that for every device. So whatever is upstream, we actually it basically is something impractical for a regular user to do. So we didn't check. You cannot checking a BIOS for each particular device. So as a result, whatever we have upstream is that when you boot it, you don't see the boot, VGA boot messages. So until when the actual device driver initializes in the guest, and at that point you see the Windows displayed. And then for ATI FirePro, this is a much more cheaper alternative at $150 each, and we would like to get that to work. And currently, we're encountering some problem with, I think, it's related to video BIOS, and we're still working on it. So one of the alternatives to work around this video BIOS problem on these discrete devices, we're thinking of is have a like dual QEMU VGA, so that during the boot time you actually see the boot messages in the VGA mode in the QEMU window, and then once the native driver initializes in the guest, and then you see it in the real display. So that's one of the alternatives we're looking into. So now we're going to talk about the stuff that's related to integrated graphics. In this case, it's Intel integrated graphics. So one of the things we discovered when we try to get things working in the Calpella is that Intel has this spec, that defines a region called IGD op region. And this is a memory area that's used to communicate between the driver and the BIOS. So actually, they're actually using some mailbox mechanism to get some information, for the driver to get information from the BIOS. And this unlike, and the way they report it is not, they don't report it through the standard PCI bar. They actually use a vendor-specific offset in the PCI config space. So yeah, the offset here is the FC of that IGD device. That's where it contains where the physical address of that op region resides. So because it's not reported in the standard PCI way, we had to make an extra call to map the guest physical to host physical mapping. So another problem we found is that these, because historically these IGD devices was part of the chipset. So when they write the driver for these devices, they have an assumption that you have the entire chipset you have access to. So a lot of them, they're not that disciplined that they only access the device they are on. They actually go and access the IOH. And in some of the later platforms from Intel where the GPU is a part of the CPU die, they actually have to access the PCH, in Linux vocabulary, they actually call it the ISA bridge. So, and then a lot of these registers where they access are actually different from generation to generation. And one of the things that we're working towards too is try to make shadow copies of these registers in the IGD device, so there's less of need to access the IOHs for those information. Another, for the PCH we talk about, the driver actually looks specifically for 01F0. So, because they assume it's a native platform. So, unfortunately, in our QEMU, the platform we're emulating, there's no 01F0. So, to work around this problem, we actually had to create a device called 01F0 and then allow the particular pass-through for those registers. Because if you don't have that, the driver actually makes an OS call that try to access this device, and the OS call will say, hey, this device does not exist, and it will return error. So for Isaku's this patch for upgrading the virtual platform to Q35, which has a 01F0 device, and that'll particularly help in this for this graphics virtualization. And the status currently is the way we run this is we actually had to run it in a kind of like a Dome 0 headless mode. We had to log in using VNC and then start the guest, and then at that point when the guest starts, they take over the graphics display. So you do the kind of the method we use is you access through the using VNC over the network. For the current support in the upstream, Zen is in Zen 4.0 and Zen Unstable. We have the support for the Quadro FX 3800 from NVIDIA. And also for some of the older Intel platforms like Q35, Q45, and GM45, which is the Montevina generation of laptops. And the current, and we also, as I mentioned earlier, we also worked on the Calpella, which is a Core i3, i5, the newer laptops just coming out recently. So we have patch for that, and also in addition, we also got Sandy Bridge to work, last week. So we have so hopefully in the future in the XCI project, once they go to the Sandy Bridge, we'll not have additional problems. It'd be relatively mature at that point. And then, as I mentioned earlier, we're still working on the ATI FirePro support. So for future work, we want to work on having, because what I was told for a while, older platforms, what happens is that when you add in the discrete graphics into a platform, they actually disable the integrated graphics. So it's kind of like it's kind of bad. You have two hardwares already. I mean, there seems to be no reason to have both of them turn on at the same time. So you can have one device used by Dome 0, the other device used by the guest, right? So, we asked around, what happens that it turns out sometime in the past, there's some thermal consideration where they don't want to turn on both at the same time. And then apparently that's no longer true. I was told that there are some OEM Calpella platforms that actually have both on. The BIOS has the option to turn on both at the same time. And for future, like Sandy Bridge, you will have these you will have an option to turn both on at the same time. Another thing we want to do is able to restart the guest. Currently, once we start the guest, actually we have no way to get it back. It may has something to do with the platform we're working on. The Dome 0 Linux doesn't have a native graphics support for the platform we're working on. And then for the discrete graphics support, we want to do the dual QEMU VGA plus the graphics pass-through, so that we can see the VGA boot messages, and then later on, once the native driver boots, you'll see the actual windows from the pass-through device. Another thing, currently when we do in this graphics pass-through environment, we pass through the USB controllers to the guest, so you have a mouse and keyboard. The problem is that when the mouse and keyboard doesn't work until you have a USB driver working, functional in the guest environment. But that does not include when you have this, let's say, a grub where you can select the kernel, which kernel you want to boot. I mean, that's usually happens if you need the support from the BIOS side. So that's the area we want to look into, so that allow you to actually select which kernel you want to boot. So in general, we also want to raise awareness of virtualization in the graphics community, right? So we're in process of getting at least from the Intel side, the Intel driver team to do their driver validation on top of Zen using virtualization. So they are actually seeing Zen as one of the validation criteria for their driver. We talked about earlier, we will try to get the future hardware to shadow the registers they need to access in the IOH config space. And also possibly report the op region in the PCI bar instead of in a vendor-specific PCI offset. And that's the end of my talk. Any questions?
So, any questions?
Okay.
So when you talk about working with the graphics driver teams about this type of project, how much understanding or how much support do you think you're getting from the graphics driver teams? And do they see it as a viable business case to be doing this, or is there education you're having to do with those teams to buy them into putting effort into this?
Yeah, so there are several levels. I mean, we do talk to the architects regularly, but one of the challenges is that these driver teams are pretty big. They span over the world, over many time zones. So one of the things we want to do, like raise awareness and do the education we want to do in those teams. Another thing is that we, as I mentioned, we kind of recruited their validation team to using this virtualization as one of the platform to validating it. So they actually, so presumably in the future, when they have a new version of driver, they'll validate it. In addition to the platforms, they will validate on the virtualization environment.
Okay. Other questions?
I have a question about dual QMVGA and discrete graphics pass-through. How do you detect the switch timings how do you detect the switching timing between QM and discrete graphics?
Yeah, this is the work we haven't done yet. So as I know, there's some for other products, VMM products. That's the kind of thing they do. So we think that's probably possible, but I don't know since we haven't done the work, we don't really know what's the actual switch timing. And you imagine theoretically, right? Right now, the reason it doesn't work, the reason you don't see the VGA right now is because what we know is, right, using QEMU VGA, you see the boot messages, right? Right. And another thing we know is that when the native driver is brought up, you see the window, right? So there's at some point the stuff will stop displaying the VGA window, and they'll have it display in the pass-through window because at that time the native driver is brought up in the guest environment.
Okay, thanks.
Hey, Alan, do you see any SRIOE type requirements making into these graphic chipsets for, running multiple VMs and things like that?
You're asking about SROV?
Yeah.
Yeah, I mean, I think there's many options people are looking into. One is similar to where Nick is doing, where you have virtual functions for graphics, where you can assign the virtual function to different guests. The other way, I think that there's stuff in the open source or other technology where you use a software-based API level sharing between two different VMs. So there are different things that people are looking at.
Okay, any other questions? I have one more question. There has been some reports on Xen list that some people got also other graphics cards working. What's your comment on that?
You say
not only the cards you listed, yeah. Some
yeah, those are just the stuff for us development, we cannot possibly buy all the cards that's out there. So those are things those are things we're going to work on, right? So for other cards that are working, I think that's fine. Maybe we can put that in the wiki and say which cards we got working and things like that.
Actually, we already have a wiki page with couple of listed adapters, but we can start adding there more.
Yeah.
Okay. Thank you.